Thank you for joining me on exercise 3G. I'm going to look at 7 part B, and this says to prove the following properties of the modulus of the complex numbers, and it's the modulus of Z1 over Z2 will equal the modulus of Z1 divided by the modulus of Z2. Well, let Z1 be A plus BI, and let Z2 be C plus DI, and let's substitute and find out the left-hand expression first. So the modulus of Z1 over Z2, and that becomes the modulus of A plus BI over C plus DI. Now I'm going to get this common denominator, get this denominator, rationalize it. So we do that by multiplying A plus BI by the conjugate of the denominator. So if the denominator has a plus, then the conjugate has a minus, and so it's C minus DI. And when you multiply this by the conjugate, it's the square of the modulus of that complex number. So I'll just put that over here. Z times the modulus of Z is the square of the Z times, the conjugate of Z is the square of the modulus of Z. So what we've got now, I will expand the numerator, and that becomes AC minus ADI plus BCI minus BDI squared over, and that becomes C squared plus D squared. And what have we got on the numerator? We will put the real components together, AC, and this term on the end here becomes, since I squared equals -1, minus BDI squared becomes minus BD times -1. So we will change that to positive BD. So we've got a plus BD as the real component, and the imaginary components BC minus AD. I will just put them both over C squared plus D squared, because when we get the modulus, that would be the square root of this first fraction squared C squared plus D squared squared, and the square of the imaginary component BC minus AD Okay, well, do we need to simplify this? Well, let's we've got the square root of A squared, so A squared C squared plus 2 ACBD plus B squared D squared and plus, and this is all over, I'm going to split it up to be the square root of the denominator let's just, for now, keep that all over C squared plus D squared squared, because they're both the same. Yeah, that's fine. Now let's expand. The second is B squared C squared minus 2BCAD plus A squared D squared. Well, that term cancels with that term. And then underneath, the square root of a fraction squared is simply just C squared plus D squared. So only the numerator will have a square root. So it's A squared C squared, B squared D squared, B squared C squared, A squared D squared, and that's all over C squared plus D squared. Right, that's the left-hand expression. Now let's do the right-hand expression. So it's the modulus of Z1 over the modulus of Z2. So we will do the right-hand side here, and so that becomes the modulus of Z1 over the modulus of Z2. So it's the modulus of A plus BI over the modulus of C plus DI, which is the square root of A squared plus B squared over the square root of C squared plus D squared Now, to see if they're both the same, what we've got underneath is the square root of C squared plus D squared. And on the left-hand side, we've only got C squared plus D squared. So what we can do here is take the numerator, A squared plus B squared, and multiply it so that we've got another C squared plus D squared. So we can get the denominator at least the same. So then now we've got a denominator of C squared plus D squared. But let's expand the top. The square root times the square root is still the square root of the product. And we've got A squared times C squared A squared times D squared B squared times C squared and B squared times D squared. Let's check these off. A squared C squared, yep. B squared D squared, yep. A squared D squared, yep. B squared C squared, yep. Therefore, the left-hand side, the left-hand expression does in fact equal the right-hand expression, and quod etrum demonstratum, what we were asked to prove. I hope this has helped. Until next time, stay happy.